Welcome to the Future Tech edition of the Finding Genius podcast. Forget frequently asked questions, forget common sense, common knowledge, or Googling for information. How about advice from a genius in their field instead? 95% of people in any profession are good enough to be qualified and licensed. 5% go above and beyond. They become very good at what they do, but only 0.1% are the geniuses of their profession. Richard has made it his life's mission to interview the geniuses of their fields in areas such as AI, 3D printing, quantum computing, blockchain and Bitcoin, and more. Don't miss out on amazing podcasts with geniuses. Review us on iTunes or wherever you listen, and go to futuretech.findinggeniuspodcast.com and subscribe today.
Hello, this is Richard Jacobs with the Finding Genius podcast, the Future Tech edition. I have Mark Z. Jacobson. His career has been focused on understanding air pollution and global warming problems, and then developing large-scale clean, renewable energy solutions to them. So he's working on a three-dimensional atmosphere, biosphere, ocean computer models. He's simulating air pollution, weather, climate, and renewable energy. And he's also working on roadmaps to transition the states to 100% clean, renewable energy for all purposes, which would be really cool. So as you know, listeners, my job here at Finding Genius is to find the geniuses in their fields. I've spoken to over 2,000 scientists, clinicians, and researchers over the years. So Mark, welcome. Thanks for coming.
Thanks for having me on, Richard.
Yeah, tell me a little bit about how did your interest grow and develop in modeling climate and pollution and things like that? Like, what's a bit of your background?
Well, when I was really young, in fact, a teenager back in the 1970s, I used to travel to Los Angeles and San Diego, and I saw that the air pollution there was really bad, and it was very difficult to see and also to breathe, and my eyes were scratchy. And I thought to myself, why should people live like this? And then, and I was 13 at the time, and I thought, maybe in the future when I grew up, I would try to work on, my career would be focused around trying to solve that problem of air pollution. And I became interested in pollution and environmental damage, and I also learned about climate as well. And that became an interest of mine too, in acid deposition and the ozone layer. And so when I went to college, I kind of tried to focus some of my the work of my classes around air pollution. Although when I was an undergraduate, there really was no, I was at Stanford University, and there was no major that I could major in that was related to it. And there were only a couple of classes here and there that actually had anything to do with it as well. And in fact, I stayed for a master's degree, and there the closest I could come was groundwater pollution. So I studied that, but I really wanted to study air pollution and ultimately climate. And so I looked around for a PhD program, and I found one at UCLA in atmospheric sciences, and I found an advisor, in fact, who was interested in somebody working on air pollution and also was a computer modeler. And so it was a really perfect fit because he had a project for me to work on, which was to study Los Angeles air pollution. And so I ended up building a computer model that turned out to be the third kind of three-dimensional air pollution model in the world at the time, which would actually track air pollutants from their emission sources, their chemical evolution in the atmosphere, their transport, their interactions with clouds and radiation, and their deposition eventually to the ground. So I learned how to computer model. I became addicted to computer modeling and I started in the modeling in 1990, and I've been working on that same model for now 30 years. And so it's gotten bigger and bigger and bigger. It started as an urban air pollution model, then it grew to a regional, then I built a global model to study air pollution, and then I used that to study climate as well. And then I connected the global model with the regional model to be able to study pollution evolution from the small scale to the large scale and vice versa, and also climate impacts of pollution. And so I've just been improving that ever since. And so it's a very detailed model that includes many, many things, but I'm really proud of it because I think it really helps to understand the atmosphere better.
So all right, so in this model, what are some of the main factors? Maybe it's obvious, but, do you include emissions from cars, power plants? Like, what are some of the main features that go into the model?
Yeah, so there are emissions, and there are different types of emissions. There's human emissions, and the human emissions I usually obtain from what are called emission inventories. So there are people whose career is based on developing emission inventories. So they develop this, they're gridded. So they're either in a city or a state or a country or the whole world, where they'll actually break the world or the state or the city up into grids of different sizes. They might be from like 1 kilometer by 1 kilometer to 5 kilometers by 5 kilometers, or even 1 degree by 1 degree on the global scale. And they obtain emissions data, and so they end up getting these huge files of emissions, and they're time dependent also over the course of a year or multiple years, and from many different chemicals and from all the different sources. So the sources are from vehicles, from power plants, from agricultural burning, even biomass burning. So those are anthropogenic or human emissions. And then there are also natural emissions, which I actually predict in the model. Like certain natural emissions are sea spray, but sea spray depends on the wind speed and wave breaking. So you can actually model that physically in one of these computer models. There's soil dust emissions is another natural emission, but that also depends on wind speed and the roughness of the surface. So you can model that. There's emissions from lightning. There are bacterial emissions from producing different gases from certain bacteria. And because we have land use types and we have different vegetation types in the model around the world, we can actually estimate bacterial emissions. There's also what are called biogenic emissions, which are from plants themselves. And so there are both natural and human emissions. So that's just the beginning. And then the model will take those emissions, they go into the air. Then there's basically a weather prediction model in there that predicts the weather, predicts the winds, the wind speed, wind direction, the temperature, the air pressure, air density, cloudiness. But in terms of the pollution, we really need the winds to move the pollutants around. And then we solve for radiation. Oh, go ahead.
Okay, so if you did a Pareto and you put the factors in order of magnitude or importance, I know that's what the model is supposed to do, but which ones are the biggest sources? Like start with the anthropogenic ones. Do you know what the true big sources of pollution are?
Yeah. Well, the human sources, there's basic categories are transportation, power plants, there's building sources, and then there's industrial sources, and then there's like agricultural sources. So transportation is one of the largest, but depending on the country, some countries, the industrial sector might be larger, but it's usually transportation. Like electricity generation, power plants is usually about 20% of end use energy. So, it's like a fifth, but transportation might be close to 30% of the total. Industry is often around 30%. And then
So the biggest is transportation. Within transportation, what's the biggest there? What does transportation consist of, and what is the biggest contributor? And, can you assign a percentage to it of emissions or pollution?
Yeah, so that's done in the emission inventories, but the possible sources are vehicles, like passenger vehicles, then there's small trucks, then there are large trucks, there are buses, there are trains, there's off-road equipment like tractors and construction machines, then there's aircraft, ships, small marine vessel boats. So every possible thing that moves that requires fuel and combustion or other type of emissions is included. The major, also we look at by chemical that's emitted. So we look at both gases and particles that are emitted. So like if you wanted to look at what's the biggest particle emitter, you would look at diesel vehicles, and that could be diesel passenger vehicles, and that could also, buses and trucks and tractors and construction machines and aircraft have, in the case of aircraft is jet fuel, but it's similar with a lot of particles. But in terms of like gas emissions, you also get those from diesel, but gasoline vehicles are more gas heavy in terms of emissions. So the actual largest source will depend on the location for sure. So there's not like one answer, but these inventories do literally break it down by each vehicle type and location, and by chemical coming from each vehicle type, and also the conditions, like cold temperatures, you'll have more emissions usually than warmer temperatures.
Well, I haven't seen this, but has anyone done a balance for an all-electric car versus a gas car? Like my guess is that an electric car maybe requires more resources, et cetera, to make in the first place. Gas car probably less. Again, it's my assumption. But then you have a very short payback period because you're not using gas, you're using electricity. it's still created by, big power plants that create the electricity. But again, has anyone done that calculation where they look at payback period to when an electric car is more efficient and less polluting than a gas car?
Yeah, there've been a lot of studies, and many of them get different results depending on the assumptions made. For example, if you just kind of look at electric car versus a gas car, an electric car has fewer parts than a gas car, and especially fewer moving parts. But it has a big battery. So the big thing in electric cars are the batteries. But there's a motor, but no engine. You don't need an exhaust system, and you don't need catalytic converter. You don't need lubricating oil and things like that. So from an actual parts point of view, there are fewer parts, but it's pretty energy intense to make all the batteries. But so a lot of it depends on how you assume the batteries are produced in terms of how much energy is going into it, or how much pollution is going into making the car. So for example, if you have like the Tesla has a battery factory in Nevada, and if that's where your battery's made, well, a lot of that electricity going into making the battery is coming from solar, so it's pretty clean. Whereas if you assume it's going to be made like in West Virginia, where there's a lot of coal, then you're going to get a different result in terms of the payback time in terms of energy. But as you mentioned, like once you produce the car, you're running on electricity, and electricity uses 1/5. You need 1/5 the electricity energy for an electric car, 1/4 to 1/5, compared with the energy in gasoline. So you're just using much less energy once you're driving that car. So there is a quick payback time, no matter what the emissions are for making.
And then what about the savings on emissions and tons of CO2, et cetera? Like, I haven't bought an electric car yet, but do they tell you that when you buy one? Or again, is there an independent calculation or set of them that says, if you drive an electric car for X number of years, you're saving this much in terms of tons of CO2?
Yeah, there are several studies like this, and most of them will show you that you're definitely saving CO2. There are a few that show you increase the CO2, but generally those are by people who don't like electric cars. But if you actually look agnostically at this, you should definitely save CO2. But that's actually, though, in my mind, is not the most important thing. What's the more important thing is you're eliminating tailpipe emissions of pollutants that affect people's health directly. So CO2 affects climate, but it's not something that when people breathe it in at the concentrations in ambient air, that it causes health problems. But all the other chemicals from vehicle exhaust do cause health problems. And it actually, like if you have the same amount of emissions from a freeway or from a roadway versus from a power plant, well, people breathe in about 30 times more of the emissions from a roadway than they do from a power plant. So that's called the intake fraction. Intake fraction from vehicle exhaust is about 30 times that of power plant exhaust. So people are arguing when you have an electric car, all you're doing is shifting the emissions to the power plant. Well, the people aren't breathing in that power plant emissions as much compared with the traffic exhaust emissions. So you're saving, depending on which country you are, thousands to hundreds of thousands of lives a year by going to electric cars. Like worldwide, 7 million people die of air pollution every year. In the US, it's only about, I should say only, but it's around 78,000, which is a lot, but compared with like China, which is over 1 million, it's smaller. So but you can get rid of pollution from traffic areas by going to electric cars, and that has such a huge health benefit and cost benefit, because actually the cost of air pollution health problems worldwide is actually much larger right now of climate damage, even though climate damage is quickly catching up.
So what, out of the United States, which states are closest to getting to, zero emissions? Are any of them close? And what's the pathway look like? If any of them have gone on this pathway, like what have been the learnings as the progression has gone ahead?
Yeah, actually, well, if we break it down into electricity versus all energy, as I mentioned, electricity is only a portion of all energy, maybe 20%. But there are some states that are 100% renewable right now. Well, there's one state, Vermont, that is 100% renewable electricity. And then there are some that are over 80% or around 80%, like Idaho, because they have a lot of hydro. And, in states like Washington State has a lot of hydro. It's pretty high up there. California is on the order of close to 45 or even close to 50% now, in terms of its electric power being from renewable sources. And there are, I think, above 50% renewable. There are around 10 states plus the District of Columbia And so, 10 out of 50 states are in their electric power sector above 50% renewable. So that's progress. That's a lot of progress. But again, we want to look at all energy. And in terms of that, we're a lot slower at transitioning because we really need to transition transportation to electric cars and buildings, get rid of gas in buildings and go to heat pumps for air heating and air conditioning and water heating, and go to electric induction cooktops, for example. So there are only a few places that actually have laws right now to transition buildings or vehicles, but there are actually 14 states and territories that have laws to go to 100% renewable electricity. So depending on the sector and the state, there has been some progress, but we just have a long, long way to go in terms of transitioning everything.
Well, again, so where is the biggest resistance that correlates with the biggest pollution? Is there resistance in the transportation sector, or like where's the problem?
I would say it's hard to say where the resistance. Well, the resistance is usually coming from people who have an entrenched interest in the current infrastructure, but you do see there's less resistance in transitioning electricity. There are places that haven't. A lot of places have a lot of laws, even if they're not 100% laws. A lot of places do have renewable portfolio standards. I think the South is probably the slowest to gravitate towards these renewable portfolio standards, but there are laws in place, and like Florida is considering 100% renewables. There are a lot of towns and cities in North Carolina that have transitioned. There are a few towns in Louisiana that have transitioned. But the thing is, it's beneficial from a cost point of view to transition. So actually the states with the most wind installed, in fact, 9 out of the 10 states with the most wind are all states that are more conservative states that would not support, for example, usually support laws for subsidizing renewables. But because the wind resources are so good and the power is so cheap, it's financially beneficial to install wind in these states. So it's really not a partisan issue, it turns out, and to install renewables. It's more of a cultural shift. Like, so people are less, even though they'll do it because it's cheaper, they might not admit that they want to do it because of partisan politics. And yet there still is a transition going on in many states. In fact, for example, Iowa has on the order of 50% of its electricity is from wind, and the same with like North Dakota, South Dakota. We're really high up there. Kansas, Oklahoma, Texas is very high. These windy states are just making a lot of money from it. So it's really financially beneficial, creates jobs, and to boot, it does reduce air pollution, and it reduces costs. So consumers like it as well.
So, all right. So again, we have some states that are naturally blessed with wind, which is great. But are there any Keystone states that are either holding out or really are critical to get to 100%? Or if they do you think that other states will all of a sudden say, all right, we could do it too? Well,
like California and New York have both committed to 100% renewables in their electric power sectors. And as I said, 14 states. One state that's having trouble is I think Ohio, which passed a law because it has nuclear power. It passed a law to subsidize the nuclear and slow down the wind and solar subsidies, or not promote them, or even inhibit. So there's a lot of nuclear seems to be competing a lot to try to. Which is kind of strange because it's so expensive for nuclear power, and most of the nuclear that's existing already, it's becoming even less profitable to run it. So a lot of nuclear power plants would shut down unless they get really huge subsidies. Like New York has 3 upstate nuclear reactors that are getting $7 billion in subsidies just to stay open, because otherwise they'd have to close. And it turns out, well, if you just took that money and you could just literally replace them with cheaper wind and solar and still have money to boot. And yet, because they're entrenched and they have a good lobbying arm, they were able to get these subsidies and slow down the transition to clean renewable energy.
Well, I had thought nuclear was feared but incredibly efficient. So what is the state of nuclear? Is it not efficient, or is this old nuclear that's not? Like, what's your observations there?
Well, if you have existing nuclear, I think so long as it doesn't require a subsidy and it's otherwise not deemed an immediate risk, those could stay open for a while until they retire naturally. But the problem is that many of them are not financially viable right now, even existing ones. And so they were asking for subsidies in several states, including New York and Ohio and other states, I think Illinois and even a few others. And it's just becoming really expensive to run them. And new nuclear is completely out of the question. It just takes forever to install. Like I would used to say 10 to 19 years, but there are several reactors that are taking between 15 and 22 or 23 years now, just between planning and operation around the world. And the cost is like 5 times that per unit energy compared to new solar or wind on a large scale. And so it's not cost effective. It takes forever. So you can't help to solve a climate problem. So we don't want to spend anything more on that technology. And that's not even accounting for all the risks it has, like meltdown risk, the weapons proliferation risk, the mining risk, the waste. What do you do with all the waste? You have to store it for hundreds. So it's really kind of a non-starter in terms of solving the climate problems, but some existing nuclear could stay if it's not requiring subsidy. But the problem is there are some plants that are asking for subsidy, and that's making it difficult to actually really solve the problem because they're so inefficient.
Are there any new sources of alternative energy that are going to be big players, or the ones we have are the ones that we need to expand upon a lot for?
Yeah, it's not like we don't need any miracle technology. Wind and solar, geothermal, hydroelectric, small amounts of tidal wave. I think the biggest growth of renewables in the U.S. and a lot of places around the world will be offshore wind, in particular floating offshore wind. Now, right now, though, that's being slowed down because the current Trump administration has decided to slow down the permitting, claiming all sorts of reasons, while they're still allowing oil and gas to be permitted offshore without the same requirements. So there's literally one wind farm offshore in the U.S. to date, and it only has a couple turbines. Whereas there are just all these companies that are just chomping at the bit to develop offshore, and that could literally power the entire U.S. if you put up enough. And because there's floating turbines, you can put them far offshore now, and it's an unlimited amount of wind offshore east and west coast. So that there's literally a bottleneck right now in really unleashing this huge production of clean renewable energy in the U.S. Due to just policy infight.
So, in terms of your modeling, what are some of the big insights that you've been getting, or that you think you'll get if you haven't gotten them yet?
Well, the biggest thing I found from my computer modeling when I was looking a lot at air pollution and climate impacts was the fact that black carbon, which is the main component of diesel exhaust and also jet fuel burning and biofuel burning and biomass burning, is the second leading cause of global warming after carbon dioxide. And black carbon is a particle component. It's not a gas. So carbon dioxide, it warms the surface of the Earth by being transparent to solar radiation, but absorbing the Earth's infrared radiation. So acting like a blanket and trapping that heat, infrared radiation near the surface of the Earth. Now, black carbon operates differently. It is black because it absorbs sunlight directly and doesn't allow that light to hit your eye. If you take out all wavelengths of light, you get black carbon. But the black carbon will absorb that solar radiation, then it will convert it to heat radiation and radiate the heat to the air around it directly. So directly heating the air with solar radiation converted to heat rather than absorbing the Earth's infrared radiation. But per unit mass, black carbon is 1 million times more powerful than carbon dioxide in the air. But the thing is that black carbon has a very short lifetime in the air compared with carbon dioxide. But it turns out, like of all the global warming worldwide, about 45% is due to carbon dioxide, and about 17 to 20% is due to black carbon. And the third is methane, is about 15%, with the third leading cause. So
is black carbon what they call or used to call soot?
Yeah, black carbon is the main component of soot, and so it is part of soot. And
what happens to it once it's spit out of an exhaust? Like, does it rise in the atmosphere, or it falls down? Like, where does it go?
Well, some of it will hit windows and roadways and trees and get absorbed, but actually worldwide, about 90% of it is removed by rain. But obviously in sunny areas, it'll stay in the air longer, but it only has a lifetime on the order of a week or two, whereas carbon dioxide has a lifetime of like 50 years, 60 years. So, but in that time, it's much more powerful at warming than carbon dioxide. So, but if you continuously emit it, which is you do when you're driving around all the time, then it's always there in the air and it's causing a lot of warming. So it's a combination of how it's short lifetime, but it's the fact that it's repeatedly emitted that allows it to be present. And so the nice thing about that is it's easy to control. I mean, if you can control the emissions of black carbon, it'll come out of the atmosphere quickly, and you can have a feedback, a cooling of the climate quickly from that component alone. Versus carbon dioxide, if you stop emitting it, you have to wait around 50 to 100 years before you see a big drop in the CO2 in the atmosphere.
Well, where does black carbon go? What are what happens to it once it's emitted? Where does it tend to accumulate?
Well, in the air, as I mentioned, it'll get removed by rain, and so rain can take it over the ocean, over land. But if it gets, and it also gets absorbed by snow too. So if it gets absorbed by snow, and let's say it goes onto snow or sea ice, it actually can warm and melt the snow and sea ice quicker. So like in the Arctic, there's some of it's being deposited on Arctic sea ice, and that's speeding up the melting of the Arctic, positive feedback. And also, if it goes onto snow, it'll melt the snow as well faster than, something else that's not absorbing, a different type of particle that reflects light rather than absorbs light. But
does it have any unintended benefits? Can it be a fertilizer? Like what's its ultimate end? What does it tend to interact with?
Well, black carbon is basically pure carbon. It's like graphite. I mean, in fact, it is graphite. So it doesn't, it can react with something else to give you something that can eventually become a nutrient, but as it really doesn't have any immediate benefits. It does have a lot of actually bad effects because, as you know, soot itself is really bad for health. In fact, because 7 million people die of air pollution each year, and 90% of those people who die from particle effects of air pollution. And many of those particles contain soot. So soot, which contains black carbon, not only kills a lot of people, but it also is the second leading cause of global warming after carbon dioxide. So conversely, if you can stop its emissions, you can not only slow global warming, but you can improve people's health. And that was the finding I found from this model, that it was also not only the second leading cause of global, controlling it is also a fast method of slowing global warming, at least to the degree that soot causes it, and can reduce health problems significantly.
So what else comes from the model that's surprising or not obvious?
Well, I've looked, for example, at the effects of particles at reducing ultraviolet radiation in urban areas. So this is maybe nerdy, but it's like, for example, there are some measurements in Los Angeles that showed reductions of ultraviolet radiation that were on the west side of Los Angeles. There were reductions due to smog were about maybe 20-30%, but then you got to the east side of the basin, they're up to 50% reductions of ultraviolet radiation. So I was trying to figure out what was causing these ultraviolet radiation reductions, because you didn't see a corresponding reduction in visible radiation. You saw only maybe 5% reduction in visible. So something was preferentially reducing ultraviolet radiation versus visible radiation. And so it couldn't be soot, because soot actually reduces all wavelengths of radiation equally. So it turned out it was due to not black carbon, but what's called organic carbon or brown carbon, which is it's like an incompletely combusted carbon as well, but it has functional groups. It's not pure carbon. It's like carbon with some oxygen, nitrogen, some other chemicals on it. And it would preferentially absorb short wavelengths of light, in other words, ultraviolet light, and allow the longer wavelengths to go through. And it turns out that as you go further east in the Los Angeles basin, these organic compounds would form. They would evolve and form as you went east, but they'd also react, and a nitrogen oxide group would add to it. And that might not mean anything, but a nitrogen oxide group basically increases the ability of a particle to absorb ultraviolet radiation. So the further east you went, there was more of this nitrogen oxide on the organics and more ultraviolet radiation reduction. So I came up with an explanation of why you get this greater UV radiation reduction in eastern Los Angeles. Now, ironically, though, because to form ozone, you need ultraviolet radiation. Because there was less ultraviolet radiation on the east side, you got little less ozone. However, because on the east side of LA, though, you still have really high ozone. I mean, it's almost the highest in the country is on the east side of Los Angeles, but it was a little bit less because of the resulting reduction of ultraviolet radiation. So ironically, when I first came out with this study, the conclusion was that there are certain chemicals in smog that were reducing ultraviolet radiation, and they also slightly reduced ozone as a result, but the ozone levels were still high. And so and it was due to some particles that you needed to add to the air, and the particles have bad health effects too. So the press got hold of this, and the headline was, "Smog is good for you."
Oh, okay.
They said smog is good for you for two reasons. It reduces ultraviolet radiation and it reduces ozone. And so everything's context.
Well, which part of ultraviolet radiation did it reduce? And again, what do you expect the effect would be upon people living in that area? Was it significant? Was it minor? And again, what part of UV did it reduce?
Well, it did reduce the UV that was normally would be received to the surface, which is UVA radiation, which is mostly tanning, but also a little bit of UVB radiation. We don't get UVC radiation, which is the shortest wavelength, the most damaging at the surface. But it would reduce harmful UV. But at what cost? The cost is you need particles to be there. You need these organic carbon particles, brown carbon particles, which kill people a lot more than the reduction in the UV. Reduction in UV, it's depending on your skin type, it could cause damage, but trivial in comparison to the health effects of the particles, which are killing in California about 13,000 people a year and causing illness to hundreds and hundreds of thousands of people more. And in Los Angeles alone, there's about 4,000 to 6,000 people dying from air pollution. So these particles, you need more particles to reduce the UVs, so it's not helping anybody in the end. And the reduction of ozone is still the highest in the country, so it's not helping that very much either. And the particles are causing more health damage than the ozone anyway.
What about so you're modeling at a state level or a city level or both, or a micro level? Like how many things
what does
your model consider?
I've done down to like street level, just a few meters resolution. Done a lot of city work and regional work where it's maybe either from 1 kilometer to 5 kilometer resolution. And then I've done a lot of work at the state and country levels of the U.S. and also global. Different types of studies for different scales, which is nice. And the nice thing about building your own model and understanding it, so you can do all sorts of things. It's like a really cool tool for me because I know it inside out, and so I can set it up to at any different any scale, and it has so many different things in it. You can just I could spend multiple lifetimes studying different things. But right now,
are there industries that you interact with? Like, how do you feel your model is being put to its best use?
Yes, I wouldn't say I interact. Like, I don't do work for industries. I do academic work and research work. I do, respond to some issues. Like, I'll give an example. Like I don't know if you remember the Aliso Canyon natural gas leak, where there's a gas storage facility down in Aliso Canyon, California, which is towards just north of Los Angeles, and it was basically a blowout of natural gas was just pouring out for 3 months of this storage facility from the ground, and just huge amounts. And it's like one of the biggest releases ever of natural gas. And it's like a big plume that got spread over California. And then there's all sorts of lawsuits that have resulted from it. So I became interested in saying, okay, well, because I have a model that's worked a lot in Los Angeles and Southern California, and why not try to simulate what's the impact of that natural gas leak on air pollution levels and short-term climate in California? Because natural gas is made mostly of methane, which is a strong greenhouse gas. Methane itself doesn't have, at low concentrations, or moderate concentrations, doesn't have health effects to a large degree, but there are other components of natural gas that do, and plus methane does react in the atmosphere and convert to over time. So it's a simple problem, but a complex problem. It's simple because there's one source that we're really looking at, but then you have to look at the evolution and the transport, and the chemistry and the radiation and the clouds, and see what the impact is. So the result was in California, there are likely additional deaths due to the resulting ozone and particulate matter from chemical production. And there's slight climate effects in different places. Eventually it got cleaned out. So, these were short-term impacts. But, this is useful information because otherwise there's no way anybody can even guess what the impact is unless you model it. I did something similar with Fukushima, the nuclear disaster, to see what was the worldwide health impacts of Fukushima. I did this for the student, John Tenho, who was graduated, but he took my model and simulated the plume from Fukushima and all the radionuclides going from there, and looking at the transport of cesium and iodine across the Pacific Ocean around the world, and what the concentrations were in different parts and different states in the U.S. of the radiation, and compared it to data, because there actually are measurements of radiation throughout the U.S. and different parts of the world.
So what's their short comment on Fukushima? How much has it impacted, and what areas? Just briefly.
So there were elevated concentrations of these radionuclides by quite a bit. We estimated they wouldn't cause much health effect in the U.S. Because the concentrations are still low, even though they're much elevated. However, in Japan and neighboring countries, concentrations were high enough to cause an estimated on the order of 1,000 additional deaths over a lifetime of people, but mostly in Asia, and which is, some people had estimated much higher, some people had estimated much lower, but they're basically, all of those other cases, when they're estimating, they're just, doing it on the back of the envelope. And this was a 3D model where we can actually compare with measurements and actually track the evolution around the world of stuff.
What, quick question. If I live in a particular city, what does the pollution around me look like, in the morning, the afternoon, the evening, and at night? What's like the diurnal variation? I know it probably depends on city, but any generalities there or interesting phenomena?
Well, generally, there are high concentrations of what are called primary pollutants in the morning. Primary pollutants are those emitted directly, as opposed to secondary pollutants, or those that form chemically in the atmosphere. So in the morning, you have two things going on. You have rush hours that put high amounts of pollution in the air directly, the primary pollutants, and you also have what's called a low inversion. Air at nighttime, the ground cools relative to the air. So when that happens, you have an inversion of temperature. Temperature increases with increasing. In other words, it's cold at the ground and it's warmer higher in the air. So the temperature increases with height. And that, when you have that situation, it's very difficult for air emitted near the surface to rise. So it stays trapped near the surface. So you have a combination of both high emissions and a low volume of air to mix the emissions into. So the concentrations are high, and that's kind of dangerous from breathing point of view. And then as the day wears on, you get the sun coming up, and that cooks a lot of pollution. So you get what are called secondary pollutants, and they form, ozone is a secondary pollutant, that usually peaks in the afternoon. However, at the same time, the air lifts, or the inversion breaks down somewhat, and the air is able to rise or dilute more. So that helps, except some of these secondary pollutants get so concentrated, even in dilute afternoon air, they're still high concentration. So you will have different pollutants in morning versus afternoon, and a lot depends on your exact location, the weather, exact weather conditions, the direction of the wind. But in some cities like Los Angeles, there's no real safe time. You're just getting different chemicals that you're breathing in the morning. Like you'll get carbon monoxide, oxides of nitrogen, reactive organic gases in the morning. In the afternoon, you'll get ozone, formaldehyde, acetyl nitrate. So it's just
Has anyone modeled what would a typical person experience health-wise or cognition-wise or whatever as they travel throughout a typical day and night in a polluted city?
I don't know about a specific, tracking a specific person and what they're breathing. I'm sure people have.
Well, an average theoretical person, what might they experience based on these changing pollutants throughout a 24-hour cycle?
Well, I think what's done more is like epidemiological studies of how does air pollution in general, if you're living in a city, affect your health. And so it used to be like in Los Angeles, it used to be living there, if you didn't smoke, was like smoking 2 packs of cigarettes a day. And many cities in the world now are like 2 to 3 packs of cigarettes a day. Now it's like more like a half a pack of cigarettes a day. But you're still losing, the average person in any big city in the U.S. is probably losing about 6 months of their due to the air pollution currently. And that's a lot better than it used to be, to 2 years. But if you're living like in many cities like in China or India right now, even way more polluted, you're probably losing 10 to.
Wow, that's crazy. Huh.
Yeah, it's amazing how the more we learn about air pollution, the more we learn how it impacts most illnesses or many illnesses, stroke, heart attack, if you have a heart attack in polluted air, you're more likely to die. Pollutants can trigger stroke. You get cardiovascular disease, respiratory illness, complications, pneumonia. Like of the 7 million people who die every year from air pollution, 20% are children under the age of 5 years old. And a lot of these are children in developing countries who are exposed to indoor burning of biofuels and coal for home heating and cooking. I mean, they're just exposed, these small bodies are exposed to high concentrations of pollutants indoors from burning fuels for heating and cooking. And then they might not die of like the respiratory illness, but they're going to die because their immune system is weaker. And so when they get a flu, they develop pneumonia and they die. So it's a very probable.
And out of the major renewables, solar, wind, geothermal, et cetera, is there any to you that stick out as having the most promise or being the closest to contributing to a significant portion of our energy?
Well, wind and solar are by far going to be the leading candidates to solve the problem, but just because the resources are so large for both and also broad, you can do it in a lot of different areas. Now, geothermal, theoretically, there's enough heat in the earth to also help solve the problem, but you have to dig way deep to get most of that heat. And there's, like in the U.S., there are like only 13 states that have good geothermal reservoirs for electricity. There's a lot of geothermal power for heat available pretty much everywhere. And so that will be exploited quite a bit. But in terms of electricity, you're not going to have a huge amount of geothermal. Hydro is pretty much tapped out. There'll be some growth, but not nearly so much as in solar. There'll be tidal and wave have potential, but again, they're more expensive still and haven't been fully corrected. So we need to solve the problem for climate change in 10 years, at least 80% of it in 10 years. And so we really need to focus on technologies that exist now and cheap. So that's going to be most.
Okay. Well, very good, Mark. It's been really good speaking to you. What's the best way for people to get in touch or to, see some of the prognostications of your modeling, to find out more about you?
Well, I have a Stanford University website, which a search under Mark Z. Jacobson can find pretty easily. There's a lot of papers by topic there. You can email me at jacobson@stanford.edu as well. I'm on Twitter with updates which is at @MZJacobson with an OM. And so I pretty much try to put out all my recent work there when it comes up. And also I'm just finishing a textbook for a class that's called 100% Clean Renewable Energy and Storage for Everything, which pretty much summarizes all our energy plans we've been developing over the last 10 years. And there is actually an online class that some people might be interested in. So right now there's a short version, just three lectures that can be linked from my website. You can find from my website. But I'm also trying to make an online class that's like a full-length class, but I might not be ready for that. That will be hopefully very low cost or free.
Well, very good. Well, Mark, thank you for coming, and I appreciate speaking to you.
Yeah, thank you for having me on your show.
You've been listening to the Future Tech edition of the Finding Genius podcast. This podcast is information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed. Review us on iTunes or wherever you listen, and subscribe today by going to futuretech.findinggeniuspodcast.com.